Hello, everyone. This is Andrew Ginter. I'm the Vice President, Industrial Security at Waterfall Security Solutions. What I have for you today is a recording of a repeat of a webinar that I did for Canada Public Safety earlier today. The webinar is on network criticality. I would have liked to record the Canada Public Safety event, but for technical reasons that wasn't possible, hence this recording for everybody who missed it. So the topic today is network criticality. This is a concept that we see some people applying consistently to their control networks. The concept is easily misunderstood, though, so I put this presentation together to hopefully clear up some of the confusion. The idea of a critical network is starting to be documented in cybersecurity standards for critical infrastructures. For example, the NERC-CIP Critical Infrastructure Protection Standards for the North American power grid, these standards define impact levels for control networks. If a worst case consequence of compromise, the worst case compromise of a control network shuts down 1,500 megawatts of power generation capacity at one power plant, that's a low impact network, anything less than 1,500 megawatts. If the worst case consequences are more than 1,500 megawatts at one plant, that's a medium impact control network. And if the worst case consequence of compromising a control network shuts down more than 1,500 megawatts at multiple power plants, that control network is a high impact network. The French ANSI standards for industrial control systems have a similar classification of 3 levels. The ANSI classification, ANSI does a calculation that's a little bit complicated, but they give examples. They do the calculation themselves for a few examples. In France, IT networks and the internet are by definition Class 1 networks. These are non-critical. Class 1 networks are non-critical. The calculation for a water treatment plant that produces drinking water for a city of 500,000 people, that calculation works out to be a Class 2 network. 1,000 megawatt power plant similarly works out to be Class 2. The French do not use the word, but I like to think of their Class 2 networks as reliability critical networks. If a reliability critical network is compromised, then essential services are no longer available. They're disrupted. In the ANSI world, the ANSI example, a railway switching system works out to be a Class 3 network. A safety instrumented system at a large chemicals plant, a plant that's near a population center, that also works out to be Class 3. Again, ANSI does not use the word, but I like to think of their Class 3 networks as safety critical. If we compromise a safety critical network, the worst case consequences are not just interrupted production. There's other unacceptable consequences like casualties at the site or environmental disasters. The common theme here in all these cases, the biggest driver as to how to classify networks, is consequences. All of these standards weigh consequences, if not exclusively, almost exclusively, certainly very heavily in the calculation. The consequences might be dollar consequences, might be the number of people impacted, but it's always the worst case consequences of compromise that determine how critical a network is in these standards. Now, what we have to remember, though, is that those are critical infrastructure standards. The calculations are based on impact on society, not impact on the business. The French example, for example, the ANSI standard, gives an example of a home appliance manufacturer. Think a factory manufacturing dishwashers or washing machines. Assume that a worst-case attack knocks out production for a week. The ANSI standards conclude there's no societal impact. Society can live without new washing machines for a week. And so the manufacturing network is only Class 1. It's non-critical. But if an attack takes down a big factory for a week, that's going to have a big impact on the business. There may be no unacceptable impact on society, but there's very much an unacceptable impact on the business. And so outside of the world of critical infrastructures, in other industries, in other kinds of businesses, these critical infrastructure calculations don't work very well. What do we see these other industries doing? We see them asking the question, just like critical infrastructure, consequences. We see them asking the question, what is the worst case consequence of compromise for each of our control system networks, or for groups of those networks together? If the worst case consequences are unacceptable, then we see those enterprises classifying those networks as control critical. Yes, there's other kinds of consequences people worry about, safety consequences, environmental consequences, but most of the time when we see this approach being used in industry, we do not see people defining 3 and 4 classes of networks. We see them defining 2 classes, control critical and non-critical. So, once we've identified our control critical networks, and we've classified them, what do we do with that? Well, all the advice out there says to protect our most important networks more thoroughly than we protect other networks. Use longer passwords, use more frequent security updates, and so on. There's no surprises here. But if that's all there was to it, well, there wouldn't be much to talk about, is there? The big difference that is emerging in how control critical networks are managed is how information is treated. In older control system security standards, the focus for control system security is protecting the information. Protect the confidentiality, the integrity, the availability of information. Or sometimes the priorities are reversed. It's not CIA, but AIC or IAC, but the priority is still protect the information. What we see in the modern standards, what we see in modern practices, is changing. The focus for information in control critical networks is not to protect the information. The focus is to protect continuous and correct physical operations. Protect physical operations from information. More specifically, protect physical operations from attacks that may be embedded in information. All cyber attacks are information, after all, and every piece of information may encode an attack. The French ANSI standards, for example, they call this out very clearly. ANSI forbids firewalls between Class 3 networks and Class 2 networks, or Class 1 networks for that matter. ANSI discourages firewalls between Class 2 and Class 1 networks. When we have to pass information between networks at different levels of criticality, and there's always information that has to be passed, when we have to pass that information, ANSI allows only unidirectional gateway technology at the connection between those networks, between networks at different levels of criticality. And this is what a lot of people find very confusing. A lot of industrial sites have a lot of industrial networks that cooperate closely with each other. The operator HMI network needs information from the communications front-end network. The historian in the DMZ network needs information from the PLC network and from the SCADA network. If everybody is unidirectionally transmitting information out of their networks and nobody can receive that information, well, nothing is going to work. And you're right. If you think nothing's going to work, you're right about that. But that's not really what ANSI is saying. What ANSI is saying, and what we are observing in people who use this critical network concept, is that firewalls are not used. They're forbidden at connections between networks at different levels of criticality. Firewalls are used routinely inside groups of networks that are at the same level of criticality. So what we see industrial sites doing is organizing their critical network into groups, into sets. A control critical network is a group of industrial networks, all of whom are managed at the same level of criticality. What ANSI requires, what other modern standards require, is unidirectional communications at the boundary between groups of networks that are at different levels of criticality. They encourage firewalls to be used inside of those groups at the same level of criticality. And, really, a lot of people ask if even this is practical. If this is, can this work? So, can it work? Let's look at the Industrial Internet of Things, the IIoT. In a sense, the IIoT is all about hyper-connected industrial systems. The trend in industrial systems, like in the rest of the world in computing, has been towards greater and greater connectivity for the last 30 years. The IIoT, in a sense, is an extreme example of that trend in the industrial space. So, let's have a look at how that actually works. I'm one of the co-authors of the Industrial Internet Consortium Security Framework. The Industrial Internet Consortium is a group of over 300 vendors that are cooperating to define how these hyper-connected industrial sites are going to work. The IIC reference architecture is the architecture that these vendors have agreed on, and that is the foundation of all of the IIC documentation and projects and designs. The diagram is what you see on the screen here on the right. This is the IIC diagram. It's even their colors. I cut and pasted. I didn't edit any of this. The industrial networks are at the bottom, and the cloud networks are at the top. Information flows are the arrows. Inside the control critical network at the bottom there, information circulates reasonably freely. Think firewalls. But at higher levels, there are white, green, and red arrows. My apologies to the red-green colorblind among our listeners. The white and green arrows are safe communications. These are the ones that are from lower levels to higher levels, and within subsystems at higher levels and between subsystems at the same level. The downward arrows are all red. These are all more dangerous than the other information flows. These are all some kind of control. Every message that is sent into a lower level of the architecture causes the computers, the next layer down, causes those computers to execute instructions that they would not otherwise have executed. Every message downward is a kind of control. And of course, the most dangerous control messages are the ones that go into the control critical network at the very bottom from higher layers in non-critical networks. So what do we do about these messages? Well, if all we have is a firewall between layers, what can we do? We can open another port. That's about it. To a man with a hammer, all the world's a nail. To a man with a firewall, all problems are solved by opening another port. What modern practice demands, what's documented in the IIC security framework, by the way, what modern practice demands is disciplined control. When we need to send control information downward, not if, when we need to send that downward, we always need to send something. We need to use the most secure, the safest way to do that that meets the business need. And that's almost never open another port in the firewall. What does it mean? Well, here's a classic design. A control network has a lot of equipment in it, including an OPC server. This is on the far left. This is the control system and the OPC server. A historian sits in a DMZ network between the control network and the IT network, and the historian regularly requests information from the OPC server in the control network and gets answers back. A business system in the IT network uses data in the historian. It uses it to do billing, to optimize operations, lots of reasons. The business system sends questions, queries into the historian and gets data back. The historian, sends its own requests to the OPC server and gets data back. So where would we draw the control critical boundary? Between each of these networks, questions and answers have to be forwarded. There's nothing unidirectional about this. The problem here is, of course, if we send polite requests from less critical networks to more critical networks, we get data back. If we send nasty requests, well, we're attacking the more critical systems from a less critical network right through whatever firewall we have in place. So what do we do about this? Well, here's one thing we can do. We can deploy unidirectional gateway technology at the boundary between the control network and the DMZ. That's this boundary right down here. That technology polls the industrial OPC server and grabs snapshots of state, tags, values, builds up a snapshot of all the tags and all the values in the OPC server, typically once a second. The gateway then sends that snapshot through the unidirectional hardware into the DMZ. The hardware is physically able to send information in only one direction. It's not physically possible for any information or any attacks to leak back. All attacks are information. No information leaks back. No attacks leak back. On the DMZ, the gateway sets up its own OPC server. The gateway is a standard OPC server that every second or so gets a snapshot of all the tags and all the values from the industrial OPC server. So now when the historian asks this replica OPC server for a value, the replica can answer with the same information that the live system would have answered. The historian gets the same answer from the replica as it would have got from the live system. And we never opened a port. We never let the requests through. We eliminated the need to send any requests from the DMZ network into the control network to retrieve data. So in terms of network criticality, what we've done is this. In effect, we've defined the control system network as the control critical network, and everything else as non-critical. And we deployed unidirectional gateway technology as the only connection between the critical network, the control critical network, and the non-critical network. So let's dig a little bit deeper into this technology. For anyone not familiar with it, the United States National Institute of Standards and Technology, or NIST as they're known, NIST published a few years ago their 882 standard for industrial control system cybersecurity. They updated that standard very recently. Revision 2 is out. In Revision 2 of the standard, NIST defines a unidirectional gateway as a combination of hardware and software. The hardware is physically able to send information in only one direction, and the software replicates servers and emulates devices. So in this diagram, this is an example of a NIST-compliant unidirectional gateway. Everything inside the red here is the gateway. It's a combination of hardware at the center here and software at the edges. The hardware includes two components: a transmit or TX module at the center left here, and this module has a fiber optic transmitter, a laser in it. The receive module or RX module at the center right here has a fiber optic receiver in it, a photocell, but it has no laser. The receive module has no laser in it, and the send module physically has no photocell on the circuit board. So together, we've got a short piece of fiber optic cable connecting the one to the other. Together, we can send from a critical network to a less critical network, but it's not physically possible to send anything back. There is no laser on the circuit board. It's not physically possible to send any signal back down this fiber optic cable. And of course, all cyber attacks are information. If no information gets back, no attacks get back. The transmit module sends completely blind. The transmit module has no idea if the receive module even has power. On the left and the right here of the rectangle, these are regular hosts. They run software. The gateway software gathers industrial data, snapshots of industrial data with normal two-way request-response communications, sends the snapshots through here, and on the outside, on the destination network, populates a replica server with those snapshots so that anybody who needs the data on the outside network, on the IT network in this example, can ask the replicas for the data and get the same answer out of the snapshots as would have come out of the original industrial systems. The net effect to this is that in this example, the IT network has access to all of the OPC data, and nothing ever gets sent back into the control network. Not a pull request, not even an acknowledgement. So, that was clever. What if, though, what if my historian is essential to operations? What if I have an optimization program running in my DMZ that uses historical data to do second-by-second optimization of my industrial operations? Now what? Well, in this case, the historian is a control-critical asset. If the historian is compromised, the optimization component, at the very least, malfunctions, and at worst, malfunctions in such a way as to send entirely the wrong commands into my control network. In this case, what we see is people deploying unidirectional gateway technology between the demilitarized network and the IT network. The gateway makes a copy of the historian on the IT. Over here on the IT network, this dashed thing is the copy. The gateway asks the historian for all of the new data, anything new coming into it, builds up a snapshot of tags and values and qualities, sends the snapshot across, and inserts the snapshot into the replica. Now, IT applications, it might be billing applications, it might be purchasing, it might be crew scheduling, all those applications, they can send their questions to the replica historian, and they get the same answers for their questions as the live historian would have provided. The gateway sends questions to the live historian. The gateway sends commands to the replica historian. Nothing from the IT network leaks back into the demilitarized zone here. So in this example, what we've done is effectively declared our control system network and our demilitarized zone together to be a control critical network. It's a network group this time, not a single network. The control critical network is a group of two networks, the control system plus the DMZ, and there's probably a firewall between there. And we deploy a unidirectional gateway as the interface from that critical network group to the IT network. And within the group, we still use firewalls. Okay, so you're thinking, enough with the easy stuff. Let's bring on the big guns. What happens if stuff really needs to get back into the control critical network? Well, concrete example, in the North American power grid, we have these things called balancing authorities. They run energy management systems. So the energy management systems on the left of the diagram here, these systems use the Inter-Control Center Protocol, ICCP. This is the protocol used to communicate between high-level control centers in the power grid. The ICC protocol is used, the energy management system uses the protocol to ask for data from power companies. So these are the power companies out here. The energy management system is using ICCP to ask for data. And the data is, if it's a city, if it's a distribution system, how much power do you need this second? If it's a generating power utility, the question is how much power are you producing in each of these geographies this second? So, the energy management system needs to know how much power is being produced, how much power is being consumed, and it needs to balance the two, because of course we cannot store grid scale levels of power yet. So, and every couple of seconds, the energy management system has to tell the generating power companies to produce a little more or produce a little less to match the load second by second. So control information is flowing into the EMS every second, and commands are flowing out of the EMS every second, and there's really no way around this. How do we deal with this? Well, in this case, what we see people do is they deploy two unidirectional gateways. Now, the two gateways here, they do not forward ICCP requests out the bottom gateway. They do not send ICCP messages out and have those ICCP answers come back in. That's not how it works. That's what firewalls do. Firewalls are routers. They forward network traffic. If the traffic is benign, they forward benign traffic. If the traffic is attacks, they forward attacks. By the NIST definition, unidirectional gateways are not routers. Excuse me. What the top gateway here does is unidirectionally replicate the ICCP servers from all of these partner utilities into the energy management network. Now the energy management system can ask the replicas for data and get answers from the replicas, the latest data, the latest snapshots of data less than a second old. Same data as they would have got if they were able to poll the partner utilities. What the bottom gateway does is replicate the energy management system out so that the partner utilities can use it, can use the replica. The partner utilities, they poll the replica and they get the same new power generation set points from the replica as they would have received from the energy management system. In both cases, the gateways pull tags and values from their sources. These are the gateway sources, on the left on the bottom, the right on the top. They push the snapshots of tags and values through, and on the outside they emulate the systems. No ICCP messages, whether they are well-formed messages or fuzzed or malformed messages or attacks, no ICCP messages are forwarded into or out of the energy management network. So what we've defined here effectively is we define the energy management network as control critical. We define it as control critical, and we deploy unidirectional gateways to protect the EMS network. One is oriented into the network and one is oriented out. More realistically, several gateways are deployed, several oriented in and several oriented out. All of these energy management systems tend to be multiply redundant because, of course, we can't afford to have all the lights go out every time some computer reboots. So, but inbound and outbound gateways is the message here. And you might ask, you might look at this and say, just a minute, is this not cheating? Gateways in and gateways out? Well, there's two answers here. The first answer, the easy answer, is that this is the safest way to get control information back into a control critical network. So, of course, we do it this way. The second answer, is this cheating? Cheating has to do with the rules. Well, let's come back to the rules. I gave a lot of examples out of the French ANSI standards. If you read those standards very carefully, it's clear that the standards are meant to evolve. The standard says when there are industrial security needs that cannot be met. Not if there are needs. When there are needs that cannot be met by the rules, the current rules, then the power companies in this example, the industrial sites, the industrial enterprises, are supposed to contact the standards authority and work something out that is safest. Not open a port on a firewall, but do something safe. So, what I'm looking forward to personally is the day when ANSI starts publishing an update to their standards, because they're doing this right now. People are contacting them saying, hey, I've got this weird need. I need a safe way to do this. Let's work something out. And ANSI is gathering this knowledge. So I'm looking forward to when they publish an update that reflects, the diversity of critical network designs that they've been coming up with and approving. Designs like this one that we see industrial sites out there coming up with and, deploying. Okay, one more, a really hard one. A manufacturer has centralized engineering. This might be a gasoline manufacturer. These might be refining plants. It might be a washing machine manufacturer. Whatever manufacturer has centralized engineering. There are no engineers at the manufacturing plants, at the industrial plants anymore. The engineers are all at head office. And they spend most of every day remoted into the control systems at one of the plants. They get into these plants through the IT network with VPNs and remote desktop. And what are they doing? They're fixing things. They're changing things. They're testing things. They're troubleshooting things. Every one of these engineers is remote logged into one or the other of these industrial networks all day long. How can we possibly do this in this critical network model? Well, what we see businesses doing is they define a control critical wide area network. The other examples I gave you were mostly local area networks. You can also define a control critical wide area network. The business purchases or leases capacity, private communications capacity. It might be MPLS or T1 or T4 or whatever the nowadays private communications is. They lease that capacity between their industrial plants. And they connect those plants not just to each other but to the head office. And they put firewalls in. And the firewalls encrypt communications between, across the wide area networks. This is private infrastructure. It's not the internet. It's not the IT network. And what the business does is it creates a little industrial network at head office. This is an extension of the industrial networks at the other sites, an extension of those networks at the head office. Most businesses will call this an operations technology WAN or an OT WAN or something like that. The business thinks of the entire OT WAN as a control critical network. Even the piece of the WAN at the head office is managed as a control critical asset. What does that mean? Well, it means that security for all of these networks has to be, and all these physical sites has to be roughly the same. Because if we let someone break into a poorly defended plant, one of these plants, now they've got access to launch attacks across all of these other sites. We have to manage all of these sites to the same level of security. At the central site here, the engineers have to badge into the area at the head office that has the computers that can access the OT WAN. What this means in practice a lot of the time is that each engineer's office, once they badge into the area, in each engineer's office there's two computers. One is an IT computer that's physically wired into the IT network that can do dangerous things like reading email or browsing the internet. And there's an operations computer. And that computer is physically wired into the control critical network. And these computers, they're often on different sides of the office. They're color coded so you don't mistake one for the other. And there's no firewalls between any of the control critical networks and any less critical network, any non-critical network. There's, there can be gateways, but there can't be firewalls. Can't be firewalls at the industrial site, can't be firewalls at the head office. There can be firewalls within the control critical network, but not at the boundary to a non-critical network. So that's what I had for you. Control critical networks are sets of industrial control network, groups of industrial control networks. The focus for security at control critical networks is preventing attack information from entering the more critical network from a less critical network, a more exposed network. Firewalls are used routinely inside control critical networks. They're used routinely outside control critical networks, but they're never used between critical networks and non-critical networks. Unidirectional gateway technology enables monitoring of industrial operations from non-critical networks. The technology also enables disciplined control of industrial networks. Disciplined control when control really is essential. You know, the difference between disciplined control and a firewall is with a firewall you open another port. With disciplined control we determine what is the minimal, necessary, efficient, safe operation, and we deploy that. And that's almost never a port open on a firewall. And for the sake of completeness here, what I've been talking about pretty exclusively is online information flows, because we're talking about networks here. Offline flows are just as important as online flows. Offline flows are USB drives, cell phones, laptops being carried into networks. My focus here has been online control, disciplined control of online information flows. A complete security program has to talk about offline flows as well. If you're interested in offline flows, if you're interested in more detail on what I've covered here, all of these topics, and then some. I've got some stuff on risk management. I've got some stuff on, defining networks, on protecting networks. All these topics are covered in my new book, Secure Operations Technology, SecOT. The book was released in January. If you would like a copy, at the time of this recording, free copies are still available from Waterfall Security Solutions, courtesy of Waterfall. You can request a free copy at the URL on the screen here. A word about Waterfall, if you'll indulge me. Waterfall is the world's leading producer of unidirectional security gateways. We invented the application of unidirectional technology to industrial systems. We have the patents to prove it. We provide a whole family of products that are designed to provide industrial enterprises with visibility into industrial operations. So we give the industrial businesses visibility, and we have a whole range of products that provide safe, disciplined control of industrial operations from outside networks when that kind of control really is needed. So again, here's what I had for you. My email address is here as well if you would like to reach out to me offline. So at this point, there were a handful of questions on the original webinar. I'm going to try and repeat the questions and remember what I gave for the answers, and then we'll sign off. So the first of the questions that came was, what about tech support? What if there's a problem at one of these sites and the support technician is at a conference in a hotel? What do we do? The first answer there is we do the minimum necessary for this scenario, and there's a number of remote support scenarios that I cover in the book. So this is one of them, and each of the scenarios has a different answer. In every case, we do the minimum. We don't just open a port, throw a firewall in, software-only protection, throw some encryption in and cross our fingers that the technician's laptop is not going to, jump across, or the bad guys on the internet are not going to be sending packets looking for vulnerabilities all day long in our firewall. We don't do that. In this case, what's the scenario? The support technician is our employee. The support technician has been through our criminal record background checks, has been through our security training programs, has been through is part of our security awareness program. Okay, this is an insider. This person knows how the control systems are designed and is familiar with the procedures for managing those networks. And what we have is an emergency. Security, the job of security, is to ensure continuous, correct, and efficient operations, to safeguard continuous, correct, and efficient operations. If we have a reliability emergency, Security had better not get in the way of us preserving efficient, correct, continuous operation. If security gets in the way of that, we've got the wrong security program. So let's have a look here. What's happening in the case of an emergency? We have a situation at the plant, it's degrading. The plant may shut down. We have an emergency. What happens is the people at the plant activate, most commonly what we observe, they activate an emergency bypass. They go to the key closet, they pull the key out of the closet, they stick it in a device, they turn the key, and they declare an emergency. They've called for help. There might be 2 or 3 other technicians driving to the site because we can't afford $1 billion site to go down. So they're driving to the site to try and fix the problem. In the meantime, we got our guru in a hotel room firing up the laptop. We have put the key in, we've declared an emergency, and what the key does, what that device does, it's a timed switch. It physically, electrically connects 2 copper wires inside the switch for a period of time, 30, 60, 90 minutes typically, and at the end of at that time physically disconnects them. So for the duration of a declared emergency, we have a 2-way connection from the internet usually into a firewall or a jump host, a heavily defended endpoint with VPNs and multi-factor authentication, etc., all of the usual protections, so that for the duration of a reliability emergency, we can have somebody remote in and try to fix what's broken while the rest of the emergency responders are driving out to the site. There's different solutions for other scenarios. So let me give you one other scenario just to contrast. Let's say there's an emergency at the site. The technical people are at the site already, and they need help. There's a cryptic error message from Windows on the screen, and they don't know what it means. They can't figure out what to do with this. And operations are starting to degrade. Everything's getting slower. So they've got a support contract with Microsoft. They call up Microsoft support. They give their contract information. They've got a voice on the phone they've never heard before, probably on another continent. And the first thing the voice asks them to do is connect their computer to the internet, off to this site that Microsoft has, and they can take control of the computer, and they can figure out what's broken for us. These people have not been through our background checks. They have not been through our security training. They've not been through our security awareness program. They are not familiar with industrial operations and rules and procedures at this site. They're not familiar with consequences of incorrect behavior. There's no way we're going to give them control of our refinery or power plant or washing machine manufacturing plant. Thank you. What we will do, though, is turn a switch and turn on remote screen viewing. We can take the machine that is showing us the error message and share that screen as a video feed, one way out through the one-way hardware, so that the Microsoft technician can log into our external website, see the video feed, and say, okay, go to the start menu and bring up system diagnostics. And this person's on the phone watching us move the mouse. No, that's communications diagnostics 2 further down. There you go, that's system diagnostics. They can see the mouse moving, they can give us advice. We're going to take the advice if we think it makes sense. These technicians are not mouse monkeys. They know what they're doing. They're going to get their advice. They're going to work with the external provider. But the external provider cannot affect operations anyway, other than giving advice over the phone, filtering that advice through the brains. This is the most advanced filter in existence, through the brains of our technicians, and they will decide if they're going to apply that advice. So that's safe remote support for outsiders, people who are outside of our security envelope. So there's a couple of examples of how to do remote support. It is possible, and it's never as unsafe as sure open another port on the firewall. There was another question. What about patch management? How do you do patch management? Well, can you do it externally? Well, this is, in a sense, it's the same question. You might say, sure, we can open up the emergency bypass once a month so people on the IT network can come in and do patch management. But is that really how it's done? What we observe at industrial sites is that nobody says, oh, look, it's Patch Tuesday, press a button, send all the patches in and start applying them. The consequences of malfunction are generally unacceptable. We see those patches, usually we see the patches being written to removable media, carried into a test bed, a heavily instrumented test bed, tested for a long time on the test bed. The test bed is instrumented to make sure that the patches have not impaired correct operation of the control system, and heavily instrumented to make sure that these patches from Microsoft or from other vendors, large and small, vendors secure and insecure, that these patches have not leaked malware into our system. Once we have done that testing for a period of days or weeks or months most often, now we can start methodically rolling out the patches to the least critical of our assets on the critical network, observe them for a time, roll them out more, and so on. So the very last steps of this process, the very easiest steps of this process, install the patches, can be done remotely if you want, but most of the process has to do with the test bed and the testing process. And so, when we have people who have unacceptable physical consequences of compromise, there's also unacceptable physical consequences of errors in the patching process. And so the patching process is done very slowly, very deliberately, very methodically, in a process that we see it called most commonly engineering change control. So it can be done, but it's different from how it's done. Nobody presses a button and says automatic updates on the control network. There was another question, can the gateways do deep packet inspection? In a sense, that's the wrong question. That's a question that you ask about firewalls. Now, there is an answer for the gateways, but let me explain for a minute about firewalls. Firewalls are routers. They forward network traffic. They forward packets from one network to another. They look at the packets. They decide, is the packet allowed? They look at the header information and say, what port is it? What protocol is it? Is it TCP? Is it port 80? Okay, then it's allowed. And this deep packet inspection, if you want to ask, is the packet allowed? Is the packet safe? You might want to look deeper into the packet to look at more of the information to decide if the packet's safe. Well, remember, unidirectional gateways, the only technology that ANSI and other standards allow between control critical network and non-critical networks. The gateways are never routers. They never forward network traffic. They never look at a packet and decide whether to send it through or not. That's not what they do. The gateways are more like Excel spreadsheets. They connect to an OPC server. They connect to a historian server. They connect to a database server. And they ask the server for information. Do Excel spreadsheets do deep packet inspection? Well, no. They ask for data. They receive the data. And they throw all the messages away. They throw all that traffic away. All they've got is a bunch of rows and columns. What the gateways do then is they take those rows and columns. They take the snapshot of data, push it through the weird one-way hardware, and on the other side, they use that snapshot of data. They insert all that data into a replica with a different set of packets, a completely different set of packets. It's queries on one side, it's insert commands on the other side. It's a completely different connection. So the short answer is no. No gateway in the world does deep packet inspection because no gateway in the world forwards network traffic. The longer answer, well, it's actually a shorter answer, but the other answer is some of the gateways out there, depending on the vendor, some of the gateways out there have the ability to inspect the snapshot of data before it gets sent through the unidirectional hardware. They might look at the data and say, just a minute, we do not want to send all of the historical data out. This data subset over here is, the trade secret control recipes. They stay in the industrial network. They're never out on the IT network where they can be stolen. There might be other rules you put in place. For the ICCP network, you might say this value here that says how much power that generator should produce, the value has to be between 0 and 300 because the generator has a rated capacity of 300 megawatts. It cannot produce less than 0. It cannot produce more than 300. So it is possible to put rules in place for some of the vendors, depending on the vendor, to inspect data in transit and make sure that the data is correct and is allowed. That's what I had. Those were the questions. Again, you've got my email there. I'm happy to answer questions by email. I'm happy for feedback on the book. If you folks actually get a copy of it and read it, I'd be delighted to hear what you say, good, bad, or ugly. Let me know. I can only produce useful material in the future if I get some feedback as to the material that I've produced already. So please let me know. If you have any other questions, send me email. Otherwise, thank you for listening, and I hope this has been useful.